In the endless dark, a stranger appeared. It entered our solar system silently, moving at an incredible speed, its origins completely unknown. This is the story of 3IATLAS, an interstellar visitor that briefly graced our cosmic neighborhood. From the silhouette of Cerro Pachon in Chile, the giant eye of a telescope turned toward a patch of sky. In the flood of data, a faint streak of light was detected. A new object, moving on a path that could only mean one thing. It came from beyond our sun's grasp. Telescopes around the world slewed into position, their massive mirrors collecting ancient photons that had traveled for millions, perhaps billions of years, through the interstellar void. Our first real look at this traveler was just a point of light, a measure of its brightness, quiet yet holding secrets from a distant star system. As we analyzed its light, a key piece of the puzzle emerged. The spectrum showed a distinct red slope, meaning its surface reflected more red light than blue. This told us it was likely covered in dark, complex organic materials, baked by eons of cosmic radiation. But something was missing. The characteristic glow of cyanogen and diatomic carbon, common in our own comets, was absent. It was dormant, a silent nucleus tumbling through space. Imagine its journey. For countless ages, it drifted between stars, bombarded by high-energy cosmic rays that slowly transformed its surface into a tough, reddish crust. It was a time capsule from another part of the galaxy. But as we watched, something strange happened. Tiny variations appeared in its spectrum. Was it truly dormant, or was it hiding its activity beneath that ancient crust? To solve this mystery, a global effort was launched. Telescopes like the SOAR telescope and the Very Large Telescope coordinated their observations, creating a constant stream of data, a round-the-clock watch on our interstellar guest. Soon, the first hints of a pattern emerged from its light curve. The brightness wasn't constant. It varied subtly, rhythmically. This was our first clue that the object was rotating, slowly revealing different parts of its surface to our view. We were beginning to decipher its spin. At the same time, the steepness of its red spectrum began to change. These subtle shifts suggested the cosmic ray-blasted surface wasn't uniform. The radiation might have even helped create the building blocks of early organic chemistry deep within its icy heart. Perhaps, buried beneath that reddish exterior, volatiles lay dormant, waiting for the sun's warmth to stir them. A storm may be hiding beneath the red crust, a silent potential for activity that we couldn't yet see. As we moved into the first week of continuous observation, the data painted a fascinating picture. The light curve, a graph of the comet's brightness over time, started to show a clear, repeating pattern. The comet spun, revealing a hidden rhythm. The regular peaks and dips weren't just random flickers. They were the direct result of its rotation, hinting at an irregularly shaped body. The way its brightness varied also gave us clues about its surface material. It wasn't just a dead rock. Something was happening. In our minds, we could picture it, a dark, elongated nucleus tumbling through space, catching the sunlight on its different faces. To be sure, observations from multiple telescopes were combined, validating the brightness changes and confirming the rotational period. Each fluctuation was a clue. Each pause was a question. What was this object made of? What story was its spin trying to tell us? We started building simulations, trying to pin down its rotational axis, to understand how its orientation in space affected what we saw from Earth. As we zoomed in on the data, we found the earliest, faintest spectral hints of emission. Something was beginning to leak from its surface. By overlaying the changing brightness with the subtle shifts in its spectrum, a new narrative began to form. The comet's secret rotation controlled its story, dictating when and where it would reveal its true nature. We plotted its brightness against its angle to the sun, seeing how the gentle warming was starting to have an effect. We could even visualize the first, almost imperceptible puffs of dust being released. The initial photometric spikes were recorded, tiny bursts of activity. The comet whispered, but it did not yet speak. Entering the second week, the whispers grew a little louder. Night after night, we captured its spectrum, and the changes became more obvious. Faint but definite emissions from cyanogen and even nickel atoms started to appear. These were the telltale signs of a comet waking up. The slope of its continuum color also continued to evolve, suggesting the surface was changing as it got warmer. We were detecting emissions so faint, they were right at the limit of our instrument's capabilities. By overlaying the rotational phase with these spectral variations, we discovered that the activity wasn't uniform. It seemed to be coming from specific spots on the nucleus, which became visible only at certain points in its rotation. Our artist impressions changed from a dormant rock to a body with the first wisps of dust jets beginning to form. Activity was stirring, almost imperceptibly. By combining the light curves and spectra from multiple telescopes, a unified picture emerged. The surface might appear calm, but deep inside, secrets were stirring. The flux of the emission lines fluctuated in sync with the rotation, confirming that the activity was tied to its spin. We could now animate the formation of a very tenuous dust coma, a ghostly halo beginning to surround the nucleus. This rotational modulation was the key. We could almost put ourselves in the shoes of the scientists, staring at the screen, seeing these anomalies and realizing what they meant. The changing slopes hinted at complex organic materials being revealed as the top layer of dust was blown away. The comet was slowly, painstakingly revealing itself. By the third week, the story kicked into high gear. The brightness spikes became more frequent and more pronounced. The comet was shedding its quiet disguise. We could finally start to visualize the dust-to-gas ratio, a crucial measurement for understanding a comet's composition. It became clear that the rotation was the primary driver of the observed activity. When an active region on the nucleus rotated into sunlight, we saw a burst of brightness and gas. Our animations now showed a more substantial dust coma expanding outward, pushed by the gentle pressure of sunlight. When we overlaid the detailed spectra with the high-cadence photometry, the connection was undeniable. Each flicker of light was a clue, each pause a mystery. The artist's impressions now showed faint but distinct dust jets erupting from the surface, becoming visible as the nucleus turned. The effect of the rotational axis was clear. It determined which parts of the comet got the most direct sunlight, acting like a switch for the activity. We plotted the emission line variations, seeing them pulse in a steady rhythm dictated by the comet's spin. A timeline animation combining data from all the telescopes showed the dramatic evolution over just a few weeks. The influence of its long journey through space was still evident. The cosmic ray-baked crust was likely insulating the interior, causing the activity to be sporadic and localized. The comet's rotation was a clock, counting down to its closest approach to the Sun. We could even simulate how the visibility of the jets changed as the comet spun on its axis. The combined light curve and spectra became a Rosetta Stone, allowing us to translate the flickers of light into a story of ice, dust, and rotation. The calm was deceptive. A new chapter for this interstellar visitor was about to begin. As we journey deeper into our observation, we condense multiple nights of spectral data into a single, evolving timeline. Watch as the comet's light signature shifts, night after night. What we see is a slow, methodical change, the very first whispers of activity, then a breakthrough. Barely perceptible at first, faint emission lines of cyanogen and nickel begin to emerge from the background noise. These are not random fluctuations. They are signals from beneath the crust, the first chemical fingerprints of gases escaping the comet's icy heart. The comet is beginning to stir, its ancient materials vaporizing into the void. Now let's dive into the details. We're animating the evolution of the continuum slope. This isn't just a pretty graph. It tells us about the physical properties of the dust particles being released. Notice how the slope changes subtly. It's our first clue about the size and composition of the dust. Zooming in, we can see the challenge and triumph of modern astronomy. Detecting these incredibly faint emission lines is like trying to hear a pin drop in a storm. It requires immense precision and sophisticated algorithms to pull the signal from the noise. But there it is, a confirmed detection, proof that something is happening. We begin to connect the dots. By plotting the spectral variations against the comet's rotational phase, a pattern emerges. The changes aren't random, they're synchronized with the comet's spin. This suggests that the activity isn't uniform across the entire surface. Instead, specific regions are becoming active as they face the sun. Imagine tiny invisible jets of dust and gas, just starting to form. These initial emissions are so faint they're almost imperceptible, a mere whisper against the silence of space. Activity was stirring, but it was doing so almost imperceptibly, building momentum with each rotation. To get the full picture, we overlay data from multiple telescopes. Spectra from one observatory, light curves from another. Together, they paint a comprehensive portrait of the comet's awakening. The light curve, which measures overall brightness, shows a steady state. The surface was calm, but the interior hid its secrets. This discrepancy is key. While the comet's brightness appears stable, the spectral data reveals hidden activity. The secrets are in the light's composition, not just its intensity. This is where the real story unfolds. Let's zoom in on the fluxes of those faint emission lines over time. We plot their intensity, and what we see are subtle fluctuations, a rhythmic dance of molecules appearing and disappearing. These are the first gasps of a waking giant. This leads to the early formation of a dust coma. Our animation shows how these initial tiny releases of dust begin to build a tenuous atmosphere around the nucleus. It's barely a shroud, more like a faint haze. But it's the beginning of the spectacular tail that will later stretch for millions of kilometers. From these spectral variations, we can infer the comet's rotational modulation. The comet's spin is the engine driving this early activity. As different parts of the nucleus rotate into sunlight, they heat up and release gas and dust. It's a pulsating, rhythmic process. Imagine being the scientist examining this data for the first time. You're scrolling through numbers and graphs, and suddenly you spot these tiny anomalies. It's a moment of pure discovery, the realization that you're witnessing the birth of cometary activity. Let's look closer at the subtle changes in the spectral slope. These slight shifts hint at the presence of complex organic molecules mixed in with the dust. These are the building blocks of life, preserved in a deep freeze for billions of years, now being released into space. The evidence accumulates, piece by piece. The comet was waking, slowly revealing itself. Each new data point is a piece of a puzzle, and the image is becoming clearer with every observation. The sleeping celestial wanderer was stirring from its long slumber. As we enter the third week of our watch, the signs become undeniable. We see distinct photometric bursts, sudden spikes in brightness that stand out against the calm background. Plotting these events, we see a clear pattern of increasing activity. The comet is no longer just whispering, it's starting to speak. We can now estimate the dust-to-gas ratio. This visualization shows us how much solid material is being lifted for every unit of gas that escapes. This ratio is crucial for understanding the comet's composition and the mechanics of its activity. The comet's rotation remains the primary driver. We emphasize how this modulation controls the timing and intensity of the activity. As active regions face the sun, they erupt, and as they turn away, they quiet down. Our animation shows the dust coma expanding in perfect sync with these brightness spikes. You can see the direct link between the release of material and the comet's overall luminosity. It's a beautifully choreographed cosmic ballet, dictated by the simple physics of rotation and sunlight. By overlaying the spectra with the time series photometry, we get a multi-dimensional view. Each spike in brightness corresponds to a change in the chemical signature. Each flicker of light is a clue. Each pause, a mystery. We are decoding the language of the comet, moment by moment. An artist's impression helps us visualize this stage. We see the nucleus shedding these faint but distinct dust jets. They are more defined now, originating from specific vents on the surface, like miniature geysers erupting into the vacuum of space. The orientation of the rotational axis also plays a critical role. Depending on our viewing angle, the same jet of dust can appear bright or faint. This geometric effect complicates our observations, but also provides valuable information about the three-dimensional structure of the activity. We can even plot the variation of those faint emission lines with even greater precision now. The fluctuations are becoming more pronounced, easier to track against the comet's rotational clock. This dance of light and chemistry is a direct window into the comet's inner workings. Coordinating observations between multiple telescopes around the world is a massive logistical effort. Our timeline animation shows how different observatories pass the baton, ensuring continuous coverage as the Earth rotates. This relentless watch is essential. We also consider the influence of cosmic rays. These high-energy particles constantly bombard the comet's surface, altering its chemistry over eons. They may have pre-processed the surface ice, making it easier to vaporize when sunlight hits. Every piece of data reinforces the narrative. The comet's rotation was a clock counting down to its full awakening. We can now create simulations that show how the visibility of a jet changes with the rotational phase. This helps us predict when and where to look for the next burst of activity, turning our observations into a targeted search. Combining the light curve and spectra into a final visualization, we see a complete picture of a system on the brink of a major transformation. The calm was deceptive. A powerful engine was revving up, preparing to put on one of the greatest shows in the solar system. Thank you for watching. Don't forget to like and subscribe for more journeys into the cosmos.